Okay, so what is total internal reflection? Hopefully at GCSE you will have covered this and you might have seen this formula before, so we're just going to do a quick recap of GCSE level TIR. So if you shine a beam of light from a ray box into a circular or semicircular block like this, it enters at 90 degrees, so it just passes straight through, and then it leaves the material and we get refraction as we saw in the previous video. And because the light speeds up, then the ray bends away from the normal. So we could look at this in terms of Snell's law. Now, if I increase the angle at some point, well, just increase it a small amount, we get a larger amount of refraction as you'd expect. And then at some point, we get the beam of light refracting along the edge. So the angle of refraction is 90 degrees. That's quite important, as we will see. When this takes place, if I was to measure the angle here, the angle of incidence, that would be the critical angle, and that varies for different materials. And if I increase the angle of incidence beyond the critical angle, then we get TIR. So this surface here, this interface between the perspex, let's say, and the air now acts as a mirror, and we get all of the light reflected. So it's total, all of the light, it's internal, so it's inside the more optically dense material, in this case perspex, and it's obviously reflection. And if I increase the angle beyond that, then I just continue getting reflection. So I is equal to R, the angle of incidence is equal to the angle of reflection. And you may have seen this calculation at GCSE. So the relationship between C and N is as shown here. So if we're given the critical angle is 43 degrees, then I can rearrange this to make N the subject, swap sine C and N is equal to 1 over sine C, and we get 1.47. So this is one way of calculating a value of refractive index by measuring the critical angle. You may be asked for uses of TIR. So there's lots of uses. The main one would be optical fibres and also endoscopes used in keyhole surgery or laparoscopy. So light beams are sent down an optical fibre inside the body, and then the reflected light is carried back up and operations can be done without cutting somebody open, so lots of benefits there. In a more simplistic way, a lot of reflectors and high-vis jackets reflect the light directly back to the source of the light, so it might be the driver of a car, so the headlights are reflected directly back, and they're very, very effective as reflectors. Right, so we have the A-level version of this formula. So sine of theta c, or sine c, that's sine of the critical angle, is equal to the ratio of refractive index, n2 to n1. So n1 is the more optically dense material, n2 is the less optically dense material. So in this case, n1 would refer to perspex and n2 to air, and theta c, as we said, is the critical angle. So we know that the TIR only occurs when the angle of incidence is greater than the critical angle, and the refractive index, or n1, needs to be larger than the refractive index n2. So we're inside the more optically dense material. So we can derive this expression here from the expression we've got for refraction from the previous video. We know at this point here, when I is equal to C, as we said previously, the angle of refraction is 90, so sine of 90 is equal to 1. So we can simplify this expression here. So if we're talking about n1, that's our refractive index. Theta 1 at this case is the critical angle, theta c. N2 is the second refractive index, the second material. And we said that sine theta 2, sine of the angle of refraction, is 1 because it's sine of 90. So we can rearrange this to make sine c the subject, and it's equal to the ratio of n2 to n1. So we can derive this expression with our general version of Snell's law. Right, so let's have a look at a worked example. So we've got an angle of incidence of 65. We have two materials. The first one, 1.5, and the second one, 1.3 refractive index. So if we were to ask to work out the critical angle, we could just use our new expression. So it's the ratio of n2 to n1. So it's really important to realise that n1 is the first material, so that's 1.5, and n2 is the second material, which is 1.3, and then s sine to the minus 1 will give us 60.1. And very typically in the exam they'll say sketch what happens to the ray of light. So we know that I is 65 and the critical angle is 60.1. So I is greater than C. So in this case, total internal reflection will occur. So we will get the light reflected back. So the angle of reflection will be equal to the angle of incidence. Right, it's your turn. So it's 4 questions. Have a read of these, pause the video, and then press play when you're ready to check your answers. Okay, question 1 is really typical, nice easy 2-mark question in the exam. So the 2 conditions for TIR, I must be greater than C, and then the refractive index N1 is greater than the refractive index N2. If we have to calculate the critical angle, that's very similar to the worked example from previously. If we know the 2 values of N, make sure you get these the right way around. So N1 is the first material, N1.6. N2 is the material that the light is passing into, 1.3, and then we can work out the critical angle. Question 3 is a variation of that. So we can make N1 the subject. So this is the refractive index of the first material. And we know the critical angle, that's fine. And it tells us that the other material, N2, is air. So we know that the refractive index of air is 1, and we can calculate the value of N1, the refractive index. And the final question, we're given the speeds, or 1 speed. Well, we know that the refractive index is the ratio of speeds of light in air to light in the particular material. So we can work out this ratio, and that's 1.2. And then we should be able to calculate the critical angle. So as we've got before, make sure you get N2 and N1 the right way around. So the first material, as it says, is 1.1. Oh, no, excuse me, the first material is 1.2, that's the one we've just found. The second material is 1.1, and we can find the critical angle. Okay, so let's think about optical fibres. So we know that the beam of light passes all the way down the core, which is made of a glass-like material. Obviously not glass because that's brittle, so some kind of plastic or perspex. And then there must be a cladding around the outside. That's really important. And we need to think about the refractive index of the core versus the refractive index of the cladding. If we want to get total internal reflection to take place here, then we have our 2 conditions, as we've mentioned already. So the angle of incidence must be greater than the critical angle, and we'll calculate that later. And the refractive index of the core must be greater than the refractive index of the cladding. If that's not the case, then some of the light will escape and it will refract out, and we won't get all the light transmitted, so we'll get a loss of transmission. Okay, so we can explain this idea of the light transmitting down the core by reflecting at each interface. So now we're going to talk about problems with transmission of light. So if you imagine we have a single pulse of light over here and it's sent down a long optical fibre. Now there's only one colour, but just to clarify the different paths that the light can take, we've shown these as 3 different colours. So the light which will travel in the shortest time takes the direct route, that's shown by the green arrow here, so that'll arrive first. And then another beam of light might follow the blue path here, which is slightly further, so that's going to take slightly longer. And then perhaps another beam of light will take this longer route where there's a lot of reflection at a greater distance, and that will arrive later. So this is referred to as multimode dispersion. It's a spreading out of the original signal. And the problem with this is that we'll have to wait until this final ray has arrived before we send the next pulse of information. So this will slow down the number of pulses we can send per second. So this problem of multimode dispersion means we cannot send as many bits or bytes per second. So what we want to do is to basically get rid of this beam of light that's taking the longer path. So if I increase the critical angle to a higher value, then it will mean that this ray may not be able to undergo TIR. So this is how we can improve the speed of transmission by increasing the critical angle. So to do that, we'll look at a calculation in the next video where we consider the relative refractive index values of the core and the cladding. But if I can get rid of this value of this red ray and maybe only allow rays to travel where the angle is greater, that means the distance travelled is going to be less, and we're going to reduce the spreading out of the data. Okay, so we'll look at a calculation in the next video which will clarify that. There is a second solution to address this issue of multipath dispersion, and this is called monomode fibres. So a typical fibre has got a relatively large core, and you can get smaller cores and then very, very small cores. So a monomode fibre means that the core is very, very small indeed. So we're looking at just a few micrometers. So these are quite difficult to manufacture, but the benefit is that we reduce this problem, because effectively all the rays of light are almost travelling the same distance. You've got the ones going directly along the centre, and then the other ones will, even if they reflect, the distance they travel, the further distance, is only a very, very small amount further. So by doing this, we reduce the spreading out of the signal, and therefore we can increase the rate of transmission. And this feels a little bit counterintuitive, because you think by decreasing the diameter, we can increase the amount of information we send. And that's absolutely the case. Right, just have a think of these 3 questions to review some of the key ideas. You can pause the video and then check your answers. Right, question 1, the 2 conditions as we said. So the refractive index of the core must be greater than that of the cladding, and the angle of incidence must be greater than the critical angle. Multimode or multipath dispersion. So it's this idea that different beams of light are travelling different distances. Some of them have to travel further, which means that the signal arrives later than other signals, and this spreads out the data. And because of that, that reduces the transmission rate. So this is a real problem. And one of the solutions, as we've said, is by thinking about the values of refractive index. So if we make them almost the same, then we increase the critical angle to as big as possible. And by doing that, most of the beams of light will not be able to travel those other paths. It'll only be the beams of light which are travelling almost directly along the optical fibre, which will be able to travel because the critical angle is so high. Therefore, we reduce the spreading out of the data.